that create 22 times 22 times 8 times 8 times 8. That would be 247,808. Okay, so you just multiply each of these. So the counting principle is super easy the way they do it. They do get harder on these, just like thinking it through it. That is why I draw these spaces on the easy ones so that you can actually think about it. So here, a certain train has 10 cars. They're being lined up on a track. One of the cars is the engine, the other is a caboose. The engine has to be the first one. The caboose has to be the last one. How many ways could the cars be lined up? Okay, I know this one has to be the engine, right? So I only have one option there, okay? I know that this one has to be the caboose, so I only have one option there. So if I have 10 total, and I take away 2 for the engine and the caboose, that leaves me with 8 cars, 8 normal cars, okay? So the way you think about this, okay, if I go to this second slot right here, if I go to this one right here, I've already used 2 of the cars, so I only got 8 left. I'll ask this question, y'all can answer it. How many different cars could I put in this spot right here?
Pretty much 8 different.
Right, there's 8 different ones, okay? So what that kind of means is I could pick one car and then 7 of you could pick a completely different car to go in that spot. Okay, now that one car is on the track. How many cars could I put in this spot? 7. So it just kind of keeps working down like that. That's the way a lot of these go. This is called, the quick way to do this in a calculator is called factorial. What that would do is actually 8 times 7 times 5 times 4 times 3 times 2 times 1. Anytime you do a factorial, it just takes that number times itself times 1 less than it all the way down to 1. So like 5 factorial, 5 exclamation mark would be 5 times 4 times 3 times 2 times 1. That exclamation mark is on your phone. That exclamation mark is on the Alex calculator. So there are some problems that comes super handy in to do. I think on this next one it actually comes handy to do. So that is, you will see like factorials a little bit in this section. Find the number of distinct arrangements of the 8 letters in slippers. 2 of the same letters are considered identical. All right, so there are 8 total letters, right? How many have repeat? The S's repeat and the P's repeat, right? So there's 2. The easy way to do this, and I kind of forgot last class, but what you want to do here is you do 8 factorial for the top one, okay? But the problem with that being my answer is that I'm not counting the S's different, okay? Like if somebody picks, I can't draw right there, but if somebody picks this first S, it is not different than somebody else picking this different S. So I have to factor that in. And the way I factor that in is since I have, you know what, I don't even want to write that. I want to write that, SP. I have 2 S's and I have 2 P's. So I have to do 1 for each of those. Okay. I have to do 1 for each of those. So I would do 8 factorial divided by 2 factorial divided by 2 factorial. This should be 10,080. And I would just do this in the Alex calculator. Okay. I pulled up another one of these because I wanted to show a different variation. You can kind of see the answer. Oh, there, I can hide it. So on this one, my total is 10, right? My total is 10. The repeats, let me see, I have N is 3 times, right? E is 3 times, and T is 2 times. So what I do in the calculator is I do the total factorial. You can see it on the right-hand side here. Total factorial, and then I divide by my repeats. I got 3 N's, 3 E's, 2 T's. So you have to divide by each of those, and that will make it come up right. So you got your N's, your E's, and your T's. So you have to. That's just the way that I remember to do that is write a little formula. Do total factorial divided by repeats factorial. And if you have multiple repeats, you can put more than 1 on the bottom. All right, permutation and combination. Oh, man, I'm sure I'm logged out of Alex. I'm going to cheat because I got the answer right here. If they start that nonsense today, they are going to start it. All right, permutation and combination. When you use permutation and combination, I'll write this down in just a second. Did I delete this picture? I thought I had one. I must have accidentally deleted it. Man. Okay, so I'll write this down in just a second once I get it in the calculator. But the way you know the difference between what we were doing previously in the permutation combination is that a permutation combination is when you have a total amount and you're choosing a certain amount out of it. So the last one we were just trying to figure out like the total amount, how many different options there were. This one here, like the first one says we have a committee of 17 people and we're trying to choose a president, vice president, secretary, treasurer, so 4 offices. So I have 17 people, I'm going to pull 4 out of those. How many different combinations could I make there? How many different ways could I fill those 4 offices? Okay, so that is how you know that you're going to do permutation or combination, because there's 2 numbers there, a total amount, you're choosing some out of it. The difference between permutation and combination is permutation, and I'll write this all down in just a second. Permutation, the order matters. Combination, the order does not matter. The first couple topics in here, it flat out tells you the order is relevant. Okay. The next topic, it says the order is not relevant. So like order is relevant would be permutation, order is not relevant would be combination. On this calculator, so you have to choose on this topic right here, you have to choose just using common sense, does the order matter or not? Okay. This example right here, the president, vice president, secretary, treasurer, the order matters, right? President is better than vice president, is better than secretary, better than treasurer. I'll go over some more examples in just a second, but just to show you the calculator so I can start writing some of the stuff down I've been saying. You had the combination button and the permutation button. They are right here. So combination, permutation, and all you're going to do here is you are going to put 17 permutation 4. Okay, so I'm choosing permutation because the order matters on the first one, and I get my answer of 57,120. On the next one, it says the pizza parlor has 12 toppings for its pizza. How many different 8-topping pizzas are possible? Well, 12, does the order matter? Does it matter if I do pepperoni here and Canadian bacon here or ham or bell pepper or whatever? It doesn't matter, right? So the order doesn't matter. Honestly, most of the time the order doesn't matter. So I use combination here. So let me write down a couple things and I'll show you where the order matters. Okay, so first of all, this was 17P4, and this was 12C8. Okay, so when to use, or I'll say this, use when given a total amount and you are choosing a group from it. Okay. So you have 2 numbers. Like that's the way I always remember it. I have 2 different numbers that I'm kind of working with here. The other ones you may have different numbers that you're working with, but here it's like 2 numbers to do the same thing. I don't know. That might confuse you with the 2 numbers there. Okay. And then the other part of this is permutation. Use when the order matters. That's fine. And combination, use when the order does not matter. So these are buttons on the calculator. Use Alex calculator. You're going to use NPR and NCR on the calculator. So you just do the bigger number first and the smaller number you just pick. The total amount would be my N, and then how much I'm choosing would be my R. Just a couple more. So like the president, vice president, secretary, treasurer, that's one option. A race, okay? These are examples of where the order matters. A race, first place is better than second place is better than third place. Password, when you write a password, it does matter what order you put them in, right? There's a sales ranking question, I think, where it says it's ranking the top 5. So like the order would matter. The weird one that they have on here is travel. Okay. If I have to go to Daytona and Miami, I don't want to go to Miami first and then Daytona. Like I'd like to go to Daytona, then Miami, right? So the travel does matter, order. So those are most of the ones where the order matters. And that should do that. Let me change these to blue. Okay, so there are 3 topics on that. I don't really do the first 2 because the first 2 like flat out tell you the order matters, the order is relevant, or the order is not relevant. For that third topic there, or the problem type 2, you have to choose whether the order matters or not. All right, so that is all of our like counting different ways. So the counting principle where you multiply everything, the permutation combination. Now we're moving into probability world. So probability to me is always, I know that you've been with me long enough to know that I don't really use math lingo. But probability to me is always what you are looking at divided by the total. Okay, I don't like probability formulas, so I try not to use them. What you are looking at in this case, they call this the event. Okay, they call this the event, and the total, they call it space. Sometimes they change the lingo based on these. Event divided by sample space. It's the number of items in the sample space, but y'all see that in just a second. Sometimes they change the lingo on these, but y'all know basic probabilities, just like kind of learning the words, but you won't have to deal with the words too much. When you get into probability rules on Thursday, when we do that, it's going to say things like, maybe you change what you're looking at a little bit. That becomes a little bit harder. There's one that kind of changes the total, but everything always boils down to that. So the sample space is all my possible options. The sample space is all the possible options. So a bag has 5 balls labeled A, B, C, D. 1 ball will be randomly picked, and its letter will be recorded. So if I draw one of these balls from the bag, I will get an A, B, C, D, or E. That's my only options. The sample space of a die. If I roll a die, I get a 1, a 2, a 3, a 4, a 5, or a 6, right? If I flip a coin, I'd get a heads or a tails. Okay, that's my sample space. The event, what we're looking at here is what's the event of choosing a B. So this would be 1. So the probability of choosing a B would be 1 out of 5. They do put those set brackets around it. I think it defaults to that. We kind of talked about sets a long time ago, but these are sets because it's a set of all the possible options or the set of the things that you're looking at, the set of the events. But this is what the basics of probability is the number of items that you're looking at, which is the event, divided by the number of items in the sample space, which is the total possible outcomes. This one's just a little bit tougher. A box has 3 cards numbered 1, 2, 3, and a bag has 3 balls labeled A, B, C. Susan will randomly pick a card from the box and record the number chosen, then randomly pick a ball and the letters chosen. So use the format 1A. So to come up with all the possible options, she could choose a 1 and then an A. She could choose a 1 and then a B. She could choose a 1 and then a C, a 2 and then an A, a 2 and then a B, a 2 and then a C, a 3 and then an a 3 and then a B, a 3 and then a C. Okay? So that would be all the possible options. And then the event is a 2. Well, I could get a 2 and then an A, or I could get a 2 and then a B, or I could get a 2 and then a C. Okay? So this one would be what, 3 out of 9? I think it's 9. To get a 2, you'd get 3 out of 9. So same as the last problem, just a little more difficult, more involved than the last one. But the sample space is all the possible outcomes. I kind of picked a terrible one for this one. I should have read it, but that's fine. So basic probability here, a spinner with 10 equally sized slices is shown. You're going to hear a lot of things like that are equally sized because you want the probability to always be the same. Like I don't want one of the red slices to be bigger than one of the blue slices. If you notice, if you ever go to an arcade or watch anything, Wheel of Fortune or whatever, like in Wheel of Fortune, the $1 million prize is like really skinny, right? And then the $200 prize is really big. So like those are not equally proportioned or equally sized slices, which changes the probability for each one. All right. So 2 are slices of blue, 8 are red. What's the probability that the dial lands on a yellow slice? Well, that doesn't really make any sense, does it? So a yellow slice, there are no yellow slices. So this would be a 0. What you're looking at divided by the total amount is 10. This would be 0 or 0%. They call this impossible, right? I cannot spin this wheel and ever get a yellow one. So this would be impossible, okay? Just because that one came up on this one, I went ahead and talked about these. If it's 100%, that means it's for certain going to happen. And then if it's less than 5%, they would just say that's unusual. Okay, that's kind of like the basic markers of the different things. So like the 100% would be something like, what's the probability that I spin this thing and it lands on a red or a blue? Well, 100% because they're all red or blue, right? All right, 12-sided die labeled 1 through 12 is rolled one time. Each number is equally likely to be rolled, so it's always going to have a sentence like that. What's the probability of rolling a number less than 9? Less than 9. So how many numbers are less than 9?
You think about like what, 8?
8, yes. So, I mean, if you need to write them out, if you need to write them all out, 6, 7, 8, 9, 10, 11, 12. I'm looking less than 9 would be these right here, right? So that is 8, and then there's a total of 12. So this, my probability would be, 8 out of 12. A lot of times, Alex will count this right and then just say you can reduce it. I don't like reducing in probability world because I like to know that I have 8 chances to win out of 12. Now, of course, mathematically, it should be 3/4. There are times that we will do decimal and even percent. So like going back and forth between all these, if you're not good at that, we're going to be doing a lot of that. I know you'll use the calculator for most of it, but I just, in probability world, it's kind of nice to not reduce. So Alex does not count it wrong on these. All right, a basket is filled with 7 white eggs, 14 brown eggs. Half of the brown eggs are cracked. An egg is randomly selected from the basket. What's the probability we get a cracked brown egg? Okay, so we got 14 brown. Half of them are cracked, right? And then there's 7 white, and we've got 21 total. We don't count this one. And we're looking for what's the probability we get a cracked divided by the total. So that would be 7 out of 21 or, once a fraction. Or 1/3. Again, I should count 7 out of 21. So a lot of this basic probability stuff right here is just reading it and making sure you pick the right thing. A lot of probability, honestly, is just reading it and trying not to overthink it. It's very easy to overthink probability. So here's a deck of cards. You do not have to know anything about a deck of cards on these problems because they give you that sheet up there. It's kind of hard to see, but at the very top right here, it does say there's 52 total cards. So we will need that information. I wonder if I can... Okay. So what's the probability that a face card is drawn? So it kind of highlights, might be hard to see on the projector, but my face cards are these right here. Okay, so there are 12 of those. So I have 12 out of 52. So you do what you're looking at divided by the total amount. The next one is a club. So my clubs are right here. Forget that I can... That's not a very good shape there, Apple. Let's try it one more time. Hey, I did it. Okay, so there are 13 out of 52 clubs, okay? But this is where you got to be careful with the wording and different things. The next one says, what is the probability that a card drawn is a face card and a club? So a face card and a club would be just these right here. So that would be 3 out of 52. So just watching the wording on these and making sure. All right, that's as far as we got in the last class, but I'm going to keep going so we can finish this. There are 2 spinners containing only orange and green slices. Spinner A has 9 green slices, 3 orange, 9 green, 3 orange. B has 7 green, 13 orange. Okay. Spinner A, event 1 is spinner A lands on a green or an orange slice. Okay, so least likely to most likely is what we're trying to do. So I'm going to find the probability of each of these before I start putting them in. Lands on green or orange for spinner A. That's 100%, isn't it? There'd be 12 out of 12, right? 9 green plus 3 orange would be 12 out of 12. That's 100%. All right, next one. Spinner B lands on orange slice. So there's 20 total. So this would be orange slice, 13 out of 20. Okay, let's go to the next one. A lands on a green, 9 out of 12. Ooh, maybe we do need to make these decimals just so we can talk about it. That would be 75. This would be 65. Y'all can double check that, but I'm pretty sure that's right. B lands on a green, would be 7 out of 20, which would be 35. Okay, so the least likely one, it looks like, would be A. Least likely would be A. Next one would be, oh, it's 4. My bad. Would be 4. I said A. Woo. 4, and then 2, and then 3, and then 1. Okay. So this is just kind of showing you, like, this is the way we talk about probability, the least likely, and different things like that. But yeah, it's probably easier just to find all 4 of those and have your numbers there, and then you can go from there to put them from least to greatest. All right, a complement. You all know what this one problem like looks super hard, but you all know what this is. Very easy. This kind of breaks down how to do it, and it does make sense. If I tell you 30% of Americans own a dog, how many don't own a dog? 70. That is the complement. You just did the complement. So the complement is whatever makes it add up to 1 or 100%. The trick on this problem right here is we have these number slices. Some of them are gray, some of them are white. The trick on this one is to pay attention to what X is. Let X be the event that it stops on a white, okay? It switches that sentence up on you, and it makes it hard, or it makes it easy to mess up. So make sure you pay attention to this. Let me do it. Sorry. Pay attention to this part right here, whatever X is, because when it switches that up, it messes with you. So X is the probability that lands on a white. So that would be 2, 5, and 6, right? That would be 3 out of 10, okay? So just, y'all know the answer to this, but if there's a 3 out of 10 chance that I land on white, then what's the probability that I land on the other one, the one that's not white? So this walks you through it. If I select all the gray ones, there are 7 of them, but it would be 7 out of 10. So the not X would be that one. So 1 minus P not X is always going to equal I think they want 3 out of 10 here, okay, which is the same as P to the X, okay? So whenever I have something and then say the not of that, it will always add up to be 100%. The probability of X is it lands on white, so the probability of not X is that it doesn't land on white. You either land on white or you don't, so it's 100% there, okay? So that's the way this one works. This answer is always one of these two. They switched this up too, I think. Sometimes that's X, sometimes it's not X. So pay attention to that. They do change that one on you. Most of y'all understand the idea of the complement. You just didn't know it was called the complement. This one will mess with you because I don't know really why, just the thought of it or the way it's laid out. So I'm flipping a coin 3 times, and this is all the different possibilities. I could get heads, tails, tails, or I could get heads, heads, tails, or I could get tails, tails, tails. So this is all the possibilities. So you just got to read these closely and figure these out. A tail on the last toss or the second toss. So a tail on the last toss or the second toss, that one happens both. Last toss, second toss, last toss and second toss, okay? So that would be all of those. It would be this one, this one, this one, this one, this one, and this one. So 1, 2, 3, 4, 5, 6. 6 out of 8 total. And again, I wouldn't even worry about reducing those down just so you don't miss it. No heads on the last 2 tosses. So that would be like this one. No heads on the last 2 tosses. Just those 2, okay? There are no H's on the last 2 tosses there. And then the last one, a tail on both the first and the last. First and the last. First and last. First and last. So 2 out of 8. Okay. So that's just kind of showing you the different outcomes, how the probability is found. Like what you're doing is you're taking all the ones that match the event divided by the total amount. Ooh, I am going to have just 5 minutes to go over some random stuff for you, I think. The last thing about probability here. Oh, man, I hope I took a good enough screenshot for this one. I think I did. Okay. The last thing about probability is called the law of large numbers. Probability always works out over the long run. It does not work out over the short run. Most of y'all kind of know this concept. Again, you just didn't know mathematically what it was. But if I flip a coin 10 times, math says that we should get 5 heads and 5 tails, right? But most of the time, we get like 3 heads and 7 tails or something like that. That is because 10 is a small number. If I flip a coin 1,000,000 times, I'm probably going to get about 500,000 heads and 500,000 tails. So what happens is it always matches the math over the long run. So it's called the law of large numbers. If I do something real short, there's a good chance that it won't match. But if I do something long, then it will. So this one says 500 times. That's a lot of times. So let's see if this works out. So for Layla's result, compute the experimental, okay? So this is where Layla is using an experiment. It's pretty easy to remember that experimental is an experiment. So like this is not the true data. This is what she did, okay? Theoretical, down here, these are the difference. This is where you use math to find it. So in the experiment, a 2 or a 5, which 75 times plus 93 would be 168 out of 500. 168 divided by 500 is 0.336. Okay. Now, if I was using math, just think of a cube. There are 6 sides, right? I can get a 2 or a 5, so I can win. I win if I get a 2 or a 5. So I got 2 chances to win. 2 out of 6 is 0.33. Okay. With the large number of rolls, there might be a difference between experimental and theoretical, but the difference would be small. Since I did it 500 times, there may be a difference, but it's going to be pretty small. I got 0.336 when I did the experiment, but I got 0.33 when I do the actual math behind it. Okay, so these numbers usually aren't the same until you do 500, 1,000, 10,000, a million. Okay, so this answer is always something like that. If there's only 20 rolls, then this answer, part C, is going to say something like, the more you do it, the closer it will get to the true value. Okay. All right. Before I keep this recording for a second, I got to pick on her for a second. Why not? Somebody. No, this gets me in trouble sometimes too. It's Black Friday, so it'll probably get me in trouble in the next 2 weeks. The first thing we started with was counting principle. This is just funny. I said it to the last class, so I'll say it to y'all too. Counting principle, right? If y'all go to your closet right now before you come to class and you see, 6 shirts and 4 pairs of pants and 3 pairs of shoes, you have 72 different outfits that you can wear. Okay, so if I divide that by 7, that's 10 weeks. It's over 2 months that you can wear with just, what I say, 6 shirts, 4 pants, and 3 pairs of shoes, right? So you can create 10 weeks worth of outfits. Okay, most of us, because we're in the top 1%, because we're in America, in the top 1% in the world, not America. Let's just do number 25 shirts and 10 pairs of pants and 8 pairs of shoes. 2,000. Let's divide that by years. You can make it over 6 years with just 25 shirts, 10 pants, and 8 pairs of shoes. You think about your closet, you'll probably have more than that. A lot of you, maybe you didn't bring that many from home, but you probably do. Okay, so you can wear 5.5 years, never wear the same outfit. So when my wife goes to the closet and says, I have nothing to wear, I need to go Black Friday shopping, I'm going to say, you want me to do the math? And then I'll get in trouble. Now, what's the female response to this? Because I know y'all thought of it. Our brains are wired differently. Oh, come on. If I have 25 shirts and 10 pairs of pants and 8 shoes, can I wear every single combination that it creates?
No.
Why? Yes, they do. Top, middle, bottom. They match. They're fine. It's good.
No.
All the guys will agree with me on that one. I got a shirt, I got pants, I got shoes. I'm good to go into public. I think I did that little workout thing that I told you about at the beginning of the semester. I did it this day, and some dude from Houston came and he's like 6'3", and he didn't wear shoes. I was like, all scared. I thought he was fixing to go wild. He didn't go too wild, but anyways, he didn't have the bottom on. At least I wear the top, middle, and bottom. Mine don't always match, but 5.5, which is what I say. Think about that again next time before you go to hit these Black Friday shopping. 25 shirts, 10 pants, 8 shoes creates 5.5 years. You never wear the same thing again. No one could ever say that they saw you in the same outfit. Okay? 5.5 years. One thing, I know it's time to go, but I got to show you this because I didn't get to do this with the other class, and it goes today. Give me a second, please. Oh, no, sorry, you're good. I thought you were the next class. Credit cards. How many digits are in a credit card? Huh? Anybody know? How many digits long is a credit card? 16, right? Okay, how many digits can I go? And you can use 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 on a credit card, right? So that's 10, and what you would do is 10 to the 16th power. So that is, I don't even know, million, billion, trillion, 10 quadrillion options on a credit card, right? Let's add in expiration date. I think it goes out 5 years. We'll even add in the CVV code. Why not? Or CVC or whatever it's called. Million, billion, trillion, quadrillion, 600 quintillion options, right? That's a lot of zeros. 3, 6, 9, 12, 15, 18, 20 zeros on there, right? 600 quintillion options. Man, I got fun things I like to talk about, but I don't have time. 600 quintillion options. I read, I don't know, way long ago that the FBI could go through all 600 quintillion with a computer in less than 6 seconds. I'm sure it's less than 0.6 seconds now. So that's what they have to do when they try to hack or different things like that. I get mad at Old Navy, as we're talking about when I have to return something to Old Navy, because they always they're like, hey, you like your MasterCard ending in 1234? Well, anybody know what the first 4 digits of a credit card stand for? It's usually what company or what bank it goes with, like a MasterCard, American Express, whatever. So if I divide that by 1,000, let's do this. So if I give them 4 digits, 10 to the 4th, right? If they know what my bank is, they got a glance at my card and saw it was U.S. Bank or Bank of America. They have a 10,000 chance more of getting my credit card, right? Okay. But then, so they say MasterCard ending in. So the MasterCard, and they see the picture of U.S. Bank or Bank of America or whatever. They know the bank. They know the last 4 too. So that's another 10 to the 4th. So Old Navy has given them 100 million more chance to steal my credit card info just by giving them MasterCard 1, 2, 3, 4, right? But then I hand them the bag because there's an online order, and they're like, sorry, we can't take it back because your address is on it. And I'm like, you just 100 million my privacy, and now you can't take my address, which, by the way, is public information. You can look up anybody's address because it's taxes. So it always makes me mad every time. I'm like, laugh at them. I'm like, you just asked for my last 4 of my credit card, but you can't throw this bag away because of my address on it. Last one, 2 years ago, I did that, and some kid's like, so you live at, and I was like, yes, that is my address. Took about 2 seconds to find it. When you buy a house, it's public information. All right, last thing. So there's 20 zeros, right? What's the UNF password? When was the last time y'all changed the UNF password? They've gotten a little better about it. 15 digits, right? We can use letters, numbers. That's 36. 36 different letters or numbers. Let's throw a couple symbols in there too. 180. So let's say So 26 letters, 10 digits. I know y'all got to go. 5 symbols, uppercase and lowercase. Okay, so I added another 26. So 206 different things I could use in a password, right? So you would do 206 to the 15th power. That is 34 zeros. Okay? I'm going somewhere with this. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Your UNF password is 85 trillion times more secure than a credit card.
Wow.
What are they going to do with your password, your MyWings account? Pay your tuition? That would be nice. What in the world? All right, we'll end on that.